Hello, my name is Maia Brodiano, and I want to talk about a statistical study of the compressible energy cascade rate in the solar wind using Parker Solar Probe and MAVEN observation. So, plasma turbulence is a multi-scale phenomenon involving structures across a wide range of spatial and temporal scales. For example, the solar wind emitting from the sun into interplanetary space, one of the most studied natural plasma, is in a turbulent state. A long-established challenge in the solar wind community is the so-called heating problem. It is manifested by the fact that the solar wind proton temperature decreases slowly as a function of the radial distance from the sun. While several scenarios have been proposed in order to explain those observations, the main candidate certainly is the local heating of the solar wind plasma via a turbulent cascade. So in this picture, the energy injected at the largest scales will cascade within the inertial scales until it reaches the dissipation scales, where it eventually be converted into thermal heat of the plasma particles. Therefore, to estimate the energy cascade rate at different scales and different heliocentric distances could bring us closer to the understanding of the turbulent dynamics of the solar wind. So, our main motivation is to investigate the energy cascade rate using the isothermal and the polytropic closure in the MHD scales, MHD or magnetohydrodynamics. So, there has been many approaches to estimate this energy cascade rate, better known as the exact laws. For example, the first generalization to these exact relations is to a magnetized plasma was made by Politano and Pouquet in 1998 using an incompressible MHD model and considering a constant density. In this way, using the compressible MHD equations and following the usual assumptions for a fully developed isotropic and homogeneous turbulence, we can obtain an expression for the exact law for the compressible MHD turbulence. And this is the expression, okay? So E is the internal energy, and F1, what we call F1 and F2 are the flux terms. S1, F1 is the modified version of the Jaglom term. And if we tend the density to a constant density, for example, the mean value of the density, F1 tends to the incompressible flux term. And F2 is a new purely compressible flux term. So the difference between the isothermal and the polytropic model is given by the internal energy, where we have this expression for the isothermal case and this expression for the polytropic case, and where we call Cs to the sound speed and Tp and Mp to the proton temperature and the proton mass respectively. So now let's begin analyzing the Parker Solar Probe observations. The Parker Solar Probe, as many of you might know, is a NASA space probe launching in 2018 with the mission of making observations of the outer corona of the Sun. So in order to analyze the solar wind turbulence at MHD scales, the dataset was divided into a series of samples of equal duration of 60 minutes. First of all, it's important to know that our dataset has many spurious data as a result of errors in the measurements of our variables and magnitudes. So to process the data, we use the next algorithm. First, we use a filter that we call the mean value filter that basically refills the spurious data with the average between the previous valid data, that is to say a non-spurious data, and the next valid data. Okay, then we use a Hampel filter. The Hampel filter uses a mobile window in order to loop through all the data. And in each window, we calculate the median and the standard deviation. This filter uses this condition up here in order to replace the spurious data. We further consider intervals that didn't show large fluctuations of the energy cascade rate over the MHD scales. Typically, we use this approximation. And finally, because most of our events didn't show high values of compressibility, where the compressibility we express like this, and watching this histogram, we decided to only choose events that whose compressibility was up to 30%. Okay, so this leaves us with a data set of 4,210 events of 1 hour duration each. Okay, so let's continue talking about our main results of Parker Solar Probe observations. First, we study the compressible energy cascade as a function of the incompressible energy cascade. And we compare two different models, the one with, of the isothermal closure and with the polytropic closure. And we call it AS 2017 and SS 21. Moreover, we use a color bar that corresponds to the level of compressibility per event. So here we can observe that the energy cascade rate increases as the compressibility increase. Okay, so this is like what we can observe. Also, there is a clear correlation between the compressible and the incompressible energy cascade rate. However, this might be because we are studying the total expression of the compressible energy cascade. So there might be a competition between the first term that, as I show you in a previous slide, is the Shaglom-like term and is like the incompressible term, and the second term that is the compressible one. Okay, so and what we can see here, what we can notice here also, and it's quite interesting, is that the polytropic model there is a subtle difference between these two models, with a greater energy in the case of the polytropic closure. Then we study the same, but we change the color bar with the heliocentric distance. And we notice, of course, that there is a strong correlation between the energy cascade rate and the distance to the sun. So the closer we are to the sun, the larger energy we have. And this is well-known results, and this is like a confirmation that we're doing. Okay, so then we study the competition between the first and the second term of the compressible energy cascade, and we found that although there is more energy around the first term, the second term is still relevant for the estimation of the compressible energy cascade. Here again, we have like more energy around the polytropic model than the isothermal one. So we are going to use numerical simulations in order to finish understanding which is the most accurate model to use. So to finish, we wanted to compare our Parker Solar Probe observation with MAVEN results, with the MAVEN observations. And MAVEN is a spacecraft orbiting Mars. I know many of you might know. Okay, so we are going to use these observations. And comparing these two figures, these two histograms, we notice that with the Parker Solar Probe observation, the density fluctuation, the level of density fluctuations, are 2 orders of magnitude higher than the MAVEN. So as a result, we have more compressible events in Parker Solar Probe than in MAVEN, since the most compressible events in MAVEN only reach up the compressibility level only reach up to 10 to 50%. Okay, so summarizing, we reported a statistical estimation of the incompressible and compressible energy cascade rate in the solar wind at different heliocentric distances. We processed the Parker Solar Probe dataset using different filters, discarding spurious and artificial peaks. This is quite important because a lot of works show results, but not the way they process data. So I want to remark that. And our observational results show an increase in the energy cascade rate as the compressibility rate increases, reaching up to 25%. Even for the nearly incompressible solar wind, we notice that the purely compressible term F2 is still relevant for a proper estimation of the energy cascade. We also compared two models, isothermal and polytropic, and we observed a subtle difference with a greater energy in the case of polytropic closure. And we investigated dependence between the energy cascade and the heliocentric distances and found a strong correlation. Finally, we compared the Parker Solar Probe results with the preliminary results we have from MAVEN observations and found more compressible events in Parker Solar Probe than in MAVEN. Okay, thank you very much.
Thank you, Maya, for your beautiful talk. There is any questions? Okay, I want to know if you compare or compare this rate with the velocity of the wind. I don't know if I think that solar probe have this data. Did you work on that?
Okay, so the velocity, we use it for the velocity of the solar wind, we use it like for calculate the energy cascade rate. Okay, but didn't analyze the velocity as a magnitude. You know, we analyze it like a total energy. But we can study that. Here we also study the distribution of the velocity of the velocity field, but we didn't pay attention much of the velocity of the solar wind.
Okay. Thank you very much.
No.
Thank you again, Maya.